I am Viridiana Tejada, and I am in charge of the organization of this webinar series from the International Society of Food Engineering. Thank you, all of you, for joining us today for our first presentation of this year. So today we're having Dr. Balasubramaniam from the Ohio State University. And before we start with the introduction, I would like you to remember remember you that our presentation lasts around 45 minutes, and then we'll have 15 minutes of questions and answers. You can you can write them in the chat if you want me to read them to the speaker, but you can also raise your hand at the end and you can ask by yourself your questions for our speaker. So as I was telling you, Dr. Bala is our today's speaker. He's a professor of food engineering at the Ohio State University in Columbus. His research focus has been on food process design, development, and validation of various thermal and non-thermal based clean food manufacturing technologies for minimally processed foods. His recent research effort focuses on development of high-pressure based ultra-shear technologies for the preservation of beverages and superheated steam for food plant sanitation. Today, I'm very happy that he can share with us a bit of his recent work and knowledge. And thank you so much, Dr. Bala. I leave the microphone. And thank you, all of you, for attending our today's webinar.
Good morning. First of all, I'd like to thank the organizers for the International Society of Food Engineers for having me part of this webinar series and share some of our research work on high pressure technologies and its applications in the food industry. And this is the brief outline. I'm going to provide a brief introduction, some of the driving forces for high pressure processing, how that affects the how the consumer trends affects the introduction of novel processing technologies, particularly on high pressure processing. We'll review some of the basic principles, followed by the equipment packaging needed, and the impact of pressure on food safety, quality, and nutrition, and some of the potential emerging applications, summary, and some references. So I think all of us are familiar with this trend. I think in the last 2 decades, the modern consumers are increasingly health conscious, and they relate their health and diet very closely. They are interested to ensure that the processed foods are safe, and especially in the last decade, there's a demand for clean label products with minimal or no synthetic ingredients. Consumers like to have fresh-like quality attributes, flavor, color, and with the increasing diversity in the society, there's new product categories can be introduced that meets the demographic, ethnic, and lifestyle changes. There's also concern about reducing the food waste and also make the food processing more sustainable by reducing the use of energy and water. So among those, we have a category of technologies called non-thermal processing technologies can be considered for potential solution. Broadly defined, the non-thermal technologies means the microbial destruction of the harmful bacteria and spoilage organisms happen through non-traditional lethal agents, because traditionally we have been doing like the high temperatures or temperatures for processing food. So the non-thermal methods use of extreme pressures, radiation, electric field, cold plasma, UV, ultrasound, gases, and so on. Among these, I think radiation has been there for quite some time, since 1960s. However, the consumer acceptance has been very limited, particularly in the United States. However, that void is now being filled by high pressure processing. So the high pressure processing has been used over the last since 1997 for commercial pasteurization applications of various value-added foods. The pressure treatment have limited efficacy on the enzymes and also have less effective against bacterial spores. One need to combine pressure and non-thermal or thermal heat so that you can able to inactivate bacterial spores. So if you broadly look at what are the potential applications of high pressure processing in the food manufacturing, there are a number of different things happening. One is the pasteurization. Basically, you apply 400 to 600 megapascal chilled or near ambient temperatures so that you can inactivate various microorganisms, and then you can able to store the product in the refrigerator conditions for about 1 to 3 months. The need for refrigeration storage is because inside the spores are not inactivated, and then it has a variable efficacy on the enzymes. You can be able to sterilize the food by combining pressure and heat between 90 to 120 Celsius, where you can inactivate bacterial spores, enzymes, and you can store them in self-stable conditions. You can also have an intermediate treatment by combining pressure and modest heat, 60 to 90 Celsius, where you can inactivate some of the psychotrophic spores, non-proteolytic Clostridium spores, and then inactivate enzymes. And with this, you can be able to make a self-stable acidified product. In fact, we have recently published research where we could show that acidified vegetables can be preserved by this way under these conditions. Other potential emerging applications include you can crystallize lipids, proteins. You can develop a continuous method for beverage processing. You can infuse nutrients and flavors, extraction, hydrolysis, under pressure, freezing, and thawing. So there are a number of pressure can be used. Like heat, pressure is a thermodynamic variable. So there are a number of unit operations can be possible. If this is the first time you are hearing about high pressure processing, you may wonder how high is the pressure. All of us live in 1 atmosphere, and the high pressure is basically, we use the term megapascal. And so 100 megapascal is roughly 14,503 psi, and typically we use 400 to 600 megapascal. It's kind of similar to taking the food, a prepackaged food, and then place under a ocean at the depth of 25 to 38 miles, and then maybe keep it there for 3 minutes so that you can kill the microorganisms without killing the natural product quality attributes. So it's a kind of extremely high pressure. And the pressure applications are kind of came from general engineering applications, like, for example, water jet cleaning, water jet cutting, crystal growth, and supercritical fluid abstractions have been used in the food industry. And of course, some of the pressure applications previously used in the food industry is very modest. Like, for example, when you do the canning operations, the pressure is very quite low, as well as some of the homogenization and other applications. Now, if you are hearing the high pressure application first time, you may ask, you are talking about extreme high pressure, will that going to crush my food? As long as the food is pretty high moisture content and packaged inside a water medium, the pressure has relatively limited macroscopic effect, even though under microscopic conditions, there may be some molecular changes. On the other hand, if the pressure is treated for like product containing air packets, like here in a styrofoam cup, you can see that it can shrink the product. So you may, for example, if you have a leafy green or any product with a very leafy or like air packets, it may not be a good candidate for high pressure processing. Similarly, if you have anything related to like a dry substances like dried cake and things of that nature, pressure is requiring moisture to transfer the effective in terms of microbiological kill. So that means it may not be a good candidate for some of the low moisture content food, or the powders are not good candidates for pressure treatment, and very limited research has been done under those conditions as of now. So what are the governing principles for high pressure processing? There are three principles can govern high pressure processing. One is the isostatic principle, the Chatelain principle, organized relationship. Isostatic principle basically kind of state that pressure is transmitted uniformly and quasi-instantaneously throughout the sample, and the process time independent of sample volume. So what that means is, we know that conventional thermal process has limitations with conduction and convection heat transfer. As a result, if you have a smaller sample, the temperature may be uniformly distributed. When you have a large size sample, there's going to be temperature gradient, and as a result, there may be non-uniformity in temperature distribution. In the case of isostatic principle, basically it says that pressure doesn't have some of those issues. And Le Chatelier principle basically say that pressure, any process associated with the reduction in volume is favored by increase in pressure and vice versa. So what happens is, when you apply pressure under normal conditions, there may be 10 to 15% reduction in volume. So as a result, any processes associated with the reduction in volume is favored by pressure treatment. And organized relationship basically apply for the traditional thermal treatment. And we will see later the pressure treatment, even though it is considered a non-thermal, you still have thermal interactions there. So as a result, we need to consider the temperature effect as well during the pressure treatment. The equipment primarily available for high pressure processing or for food pasteurization applications, they are primarily available in the form of vertical machines or horizontal machines. So a View, hyperbaric, then Uday are some examples of the companies which make commercial scale equipment. And the vertical equipment here, for example, may be used for seafood applications, whereas the horizontal equipment may be applicable for prepackaged food, where the product is introduced from one end of the conveyor belt, and then they're received in the other end of the conveyor belt. And typically, the volume right now for the high pressure vessels are about 525 liters, and 10 to 70 million pounds per year products are typically processed. So this just to illustrate the typical components of pressure vessel. You have a pressure vessel with the enclosure, you have an intensifier, and then you also have some water tank which act as the pressure transfer fluid. And basically you take the raw product, package it, and then you maybe precondition it, and then load inside the pressure vessel, and then the pressure transfer fluid is filled inside, and then you're going to hold it for a certain time, and then you discharge pressure, and then you're going to unload the product. So this is a typical operation of the pressure during a pressure cycle. And this illustrates some of the sample baskets, how they are being loaded from one end of the pressure vessel and then received in the other end of the pressure vessel, and then go through some drying step before the product is distributed. Packaging plays an important role during the high pressure processing. At least one interface of the package has to be flexible. PET, PE, PP, EVOH films are some of the examples of commercial products, packaging films that may be used. And you want to minimize the headspace. And like food material, the pressure can also influence the packaging material, the oxygen and moisture transmission barrier properties, and there may be some impact on mechanical and mass transfer migration properties. So those things need to be considered before you selecting the suitable packaging material. Pressure is relatively relatively cylindrical in nature, And as a result, how we effectively use the pressure system is important. So this kind of illustrates how different shaped containers affects the vessel filling efficiencies. So you can, for example, if you are using a bag in a box, big pouches, you may quite effectively use maybe 75 to 85%. On the other hand, if you're going to use some of the cups, consumer size, you may have an efficiency about 35 to 40% of filling efficiency. So this is something that needs to be considered as well. The commercial equipments are about 525 liter capacity. The cost may vary depending on the options you choose, and you may be able to produce 10 to 70 million pound per year. And the processing cost, depending on number of factors, can vary from 3 to 10 cents per pound compared to a thermally processed product. And then if you look at the breakdown of the cost, pressure vessel is going to be one of the more expensive part, 50 to 60%. The pumping system may be about 30%. The instrumentation controls maybe about 10 to 15% of the cost of the system. So being a new processing technology, we need to consider the impact of lethal agents, pressure, heat, the packaging, and also since the consumer is interested in less chemicals in the processed food, we need to consider how natural additives and ingredients interact with the pressure treatment. And then we need to consider against microbiological safety, quality, shelf life, and also potential health promoting opportunities with these pressure treated products. Now, if you are first time doing high pressure processing, how are you going to validate this, and how do you identify proper microorganism for your studies? First of all, you need to identify what's the most resistant pathogenic organism of public health concern, and then how much log reduction you need. You need to also consider the impact of food matrix, the injury and recovery of the injured bacteria, and so on. Some of the composition, pH, water activity, all those things can play a role in these conditions. And it is important to select the organism based on your regional conditions rather than looking at the publication. So for example, a study conducted 100 different strains of Listeria monocytogenes at 350 megapascal 10 minutes. You probably see that some strains have no reduction, some strains have 6.75 log reduction, some strains have 3 log reduction. So if you choose 6.75 log reduction, and if you happen to be one of the strains which is have only 2.5 log reduction, you may have a food safety problem. So you need to pay attention to the what is the pathogen of concern in your specific region. And you also need to consider the injury and recovery of the bacteria so that you can be able to make sure that by selecting proper temperature, the more than 5 log reduction of the dead bacteria is achieved under these conditions. High pressure pasteurization can be done typically at ambient or chill conditions, and generally bacteria spores are not inactivated. And then if you look at the meat products, you basically look at Listeria as one of the key pathogen of concern with the 500 to 600 megapascal, and it can be used in a variety of different products. On the other hand, if you look at the seafood, you can have modest pressure treatment, 200 to 500 megapascal, where you want to control the Vibrio paramelliticus. And fruits and vegetable products, dairy products, have E. coli, Listeria, Salmonella, and some of the pathogens of concern. And here are some of the example products of the meats. These are like a variety of juices, beverages, fruits and vegetable type products. And this is just some of the ready-to-eat type products. And these are some of the seafood type products, lobsters, oysters, and so on. So these are some of the examples of products commercially in the market. High pressure processing can be combined with heat so that you can inactivate some of the psychotropic spores, non-proteolytic Clostridium botulinum, and under these conditions, proteolytic Clostridium botulinum may survive. So this mild treatment, where maybe you're talking between 400 to 600 megapascal, maybe up to 70 Celsius, this may be used for extended shelf life products or acidified products. And when you increase the temperature further, 90 to 120 Celsius and 400 to 600 megapascal, you can able to inactivate Clostridium botulinum spores, enzymes, and you can create commercially sterile ambient stable products. And FDA issued no objection to 2 industrial petitions during the past 5 years. As of now, there are no commercial products in the market. Now, when you consider external shelf life product or pressure assisted thermal sterilization type product, temperature plays an important role. And pressure and temperature are part of the thermodynamic parameter, and pressure primarily affects the vibrational kinetic energy. On the other hand, pressure affects the changes in volume and entropy. So each has a different effect, and that's something needs to be considered. So when you're doing high pressure processing, you are building the pressure and then holding the pressure for some time, and then you're going to depressurize it. Depending on whether you sterilize it or pasteurize, the product may be pre-chilled, or you may be preheating to certain temperature, and then it's loaded inside the pressure vessel. As the pressure is building, there's going to be temperature increase because the product is compressed and the volume is reduced by 15%. That brings the molecules together. As a result, there's going to be some temperature increase, and then you may be holding that temperature, or there may be some temperature loss depending on the insulation characteristics of the vessel. And then after depressurization, the temperatures goes back to initial conditions. The heat of compression parameters for water varies as a function of initial temperature. You might have heard that heat of compression water is 3 degrees Celsius. That's typically at 25 degrees Celsius. But if you process at 70 degrees Celsius, the value can go as high as 5 degrees Celsius. Carbohydrate proteins have heat of compression values similar to water. On the other hand, fats and oils have higher heat of compression, 8 to 9 Celsius. The engineering properties of food, such as thermal conductivity, specific heat, compressibility, all can be influenced by the pressure and temperature treatment, and that should be studied so that we can able to have a proper control over the uniformity of the pressure treatment. This slide just illustrates the importance of knowing how pressure, heat interact different microbiological chemical reactions. So this is a M2 chemical marker with whey protein gels with 0.1 megapascal atmospheric condition, 105 degrees Celsius. The marker yield increases with increasing holding time. On the other hand, if you look at pressure treatment at 350 megapascal or 700 megapascal at 30 Celsius, you can see that pressure treatment suppresses the formation of marker yield. On the other hand, if you increase the temperature to 105 degrees Celsius, 350 or 700 megapascal, there's an intermediate marker yield formation. This just shows that you need to consider both pressure and temperature effect on any chemical or microbiological reactions. And this just illustrates that how Bacillus cereus spores are inactivated at atmospheric condition 85 degrees Celsius. You may need about 160 minutes to achieve about 7 log reduction. On the other hand, at 600 megapascal, 85 degrees Celsius, you can do that in 4 minutes. At reducing the temperature to 60 Celsius at 600 megapascal, increase the process time by 7 minutes. And so this kind of illustrate the integration of lethal effect of pressure and temperature needs to be studied. So the pink line here just shows that thermal treatment 105 degrees Celsius, 103 Celsius for 5 minutes. Obviously, there's no inactivation of bacterial spores with the heat under those conditions. On the other hand, when you combine with pressure and heat, 600 megapascal, 103, 5 minutes, you can see certain accumulated lethality. And if you increase the pressure treatment 600 megapascal, 116 Celsius, 5 minutes, this is the accumulated authority that considers both pressure and temperature. On the other hand, the thermal Wanley effect, you can see that this is kind of significantly increased from here. And if you were to do this experiment at 600 megapascal, 121 Celsius, you can see that these two lines merges, indicating that pressure become less effective at 121 Celsius, temperature becoming a dominant factor. So there is an opportunity for a window where pressure and temperature can be effective and contributing to microbiological lethal effect, and that should be considered. We also need to increase the synergy of using natural antimicrobial compounds such as essential oils, fatty acids, bacteriocins, and so on, so that you can increase the lethal effect of pressure and heat. And this way you can be able to reduce the process severity, extend the shelf life at a reasonable cost. And so, for example, we have done some studies where we looked at the inactivation of amyloliquefaction spores by combining with chitosan licorice extract or chitosan licorice extract combinations. So the raw sample started with the 8.2 log reduction. When you have only pressure treatment, temperature treatment, 600 megapascal, 103.5 Celsius, 3 minutes, you had about 4.5 log reduction. On the other hand, when you combine with the pressure, temperature, and natural antimicrobial compounds, you had subsequently only 2.3 logs left or survived. It's important to balance between the food safety and quality. Even though we are interested in minimally processing, we cannot just ignore the safety. So if you just move away from this clip, you may have unacceptable quality. On the other hand, if you, in the interest of maintaining the quality, if you move towards the clip, the tip of the clip, you may going to fall down. So you need to make sure that your safety is important, and then you kind of needs to consider the quality, and then how the preservation of quality, health promoting compounds can be considered, and so on. And pressure treatment basically can potentially used for preserving health promoting compounds. So for example, it has a minimal effect on vitamins and flavor compounds, and there are opportunities to use the pressure treatment as a chemical hydrolysis, conversions under pressure. And this research is kind of just beginning, so we need to have more research needed. So for example, we looked at looking at the ascorbic acid in pineapple juice, and you can see that pressure treatment at atmospheric ambient temperatures has relatively no effect on the raw juice. On the other hand, if you're going to add heat, different temperatures, 75, 85, or 95, depending on the extent of heat added, you're going to have more destruction of ascorbic acid. Similarly, we have done some studies where we found that the bioactivation of glucosinolate to isothiocyanate can be facilitated by pressure treatment, because consumers often prefer raw sprout for healthy reasons, but you also have a food safety reason. So there may be opportunity for preserve the safety of the product as well as make it more healthy. This slide just shows this inactivation or the formation of furan by selected combination of temperature, pressure assisted thermal processing, and high pressure processing. The red line shows that formation of furan is increased in different substances where depending on the type of food matrix. On the other hand, the black line just shows the pressure treatment, and pressure treatment at ambient temperature or chilled conditions, and you can see that it's almost below the detection limit. Similarly, you can be able to control the immunoreactivity or allergenicity in almond milk with the appropriate formation of pressure temperature treatment. And with the increased interest in commercialization of the beverages, there's an interest to develop continuous pressure treatments for liquid foods. And we have been doing some studies where we are taking high pressure, apply them under pressure, and then it's going to be discharged through a set of homogenization type valve. And then you also have a whole tube, and then followed by aseptic cooling. And we are trying to understand what are the forces acting on the different shear valves and how that affects the food safety and quality. We'll keep you those research progress at future meetings. It's important to understand the limitations of the high pressure technology. So we talked earlier that it may not be quite effective with the low moisture content type products. And similarly, the pressure treatment may not be effective in heavy metals and pesticide residues that may be found in raw ingredients. So we need to make sure that we properly select the ingredients. Consumer acceptance is another key, and it's important to communicate the benefits and risk of novel processes such as consumers so that they can be able to understand this. In the era of social media, consumers hear so many inaccurate conflicting information. So academic researchers, industrial researchers together can provide clear, understandable, credible scientific information so that consumers can have a trust on the technology. And again, being a new processing technology, the selection of proper products is important. High pressure processing is a novel technology, so it's important to identify some unique products which doesn't exist, so that the consumer willing to try and pay for some additional cost associated with the technology. Some of the future research needs, I think there's a lot of opportunity in the process design and development, as well as process uniformity, and some of the clinical studies, as well as process ingredient interactions. In summary, like I think like heat, pressure is a fundamental thermodynamic variable. It has a versatile applications. In 1997, pressure pasteurized products introduced as a food safety technologies. Today, it continued to get the imagination of the food processor because there are a number of applications, including clean label products, can be done with this technology. It is a teamwork. You need a transdisciplinary team of food engineers, product developers, microbiologists, nutrition science. And also there's an important to have collaboration among academia, equipment provider, and the food processor so that we can develop the underpinning high pressure science and engineering. And we also train the next generation of workforce and industrial leaders. And here are some selector references you may find useful. And with this, I conclude my presentation. Happy to answer any questions.
Thank you so much, Dr. Bella. We do have some questions from the audience. They are asking, what's a clean label product?
So clean label products, maybe this is a trend, I think maybe primarily seeing in the US and maybe some of the European countries, where the consumers interested in removing or reducing, introducing the artificial or synthetic chemicals, and they like to see ingredients used in the formulated products are more natural and easy to understand.
They also are asking if this technology can be used for coconut milk.
Which milk?
Coconut.
Coconut milk? Yes, I think coconut milk, basically it has a high water content, so it can be used. In fact, I think on a related topic, coconut water is one of the products people trying to use high pressure so that you can able to enjoy, consumers enjoy the coconut water. So coconut milk definitely can be potentially used.
Also, could you please tell what is the main cost of the equipment, the vessel itself, pumps, actuators. Maybe which one would be the initial investment for?
Right. I think the commercial scale vessels, like maybe depending on the volume, like the industrial scale vessels, probably depending on your need, can be as high as low as 55 liters or maybe 525 liters, and anywhere in between, maybe 300 liters and so on. Now, the cost of the machine probably depends on how much bells and whistles, extent of automation, process control you desire. So it can be anywhere between $2 to $5 million, depending on various options you select. On the other hand, if you select a lower volume like 35 or 55 liters, the cost can be less than $2 million. So it can be reasonable under those conditions.
And do you think that this could be reduced in the future?
Yes, I think in early 1990s, when the high pressure processing was introduced, the equipment expenses were maybe 5 to 10 times more, because they were more like prototype equipment, one of a kind equipment. Now you have multiple equipment providers, and they were also making a lot of innovations, so that reduced the equipment cost. With the more and more industrial adaptation, the cost of the equipment can further go down.
Thank you. They're also asking if are there any commercial PATP equipment? If not, is there any lab scale equipment in the US available for validation or studies?
So I think the commercial PATP equipments are not available. I think it's one of those things where the equipment providers are waiting for the commercial interest in this technology, vice versa. So I think eventually this will happen. Yes, I think there are many laboratories, including Ohio State University, have the temperature control capability. So this can be done under those PATP type conditions.
Also, the audience would like to know if high pressure processing has been studied against aflatoxins or some other allergens.
So the question is, are you talking, is the high pressure processing has been studied for allergen type applications?
Yes, I think that yeah, that's the question.
Right.
Aflatoxins.
Right. I think there are some limited studies have been conducted with the high pressure processing and allergens, but they are not necessarily comprehensive. So there's an opportunity for doing more systematic studies under these conditions. But the initial reports indicates that high pressure processing seems to be effective in reducing some of the allergenicity of different food materials.
Could you please, Doctor, show us the slide 11 again? I have a question from NITR, which says, well, first, he wants to see the slide 11, and also he is asking about establishing a commercial scale in India.
Okay, so slide 11. Is this a slide?
Yeah, I think so. Could you please just kind of re-explain it?
Okay, sure. So if you look at inside, you probably have a pressure vessel, which is in the horizontal configuration, and it has safety enclosure. And typically, the product may be introduced using a conveyor belt and then placed inside a carrier baskets. So in this slide, it shows that maybe 4 or 5 carrier baskets are queued up for loading inside the pressure vessel. When you're ready to run the machine, these is going to go inside and then going to be the vessel is going to be closed. And then you have intensifiers here, and the water serves the pressure transfer fluid. So the intensifier is going to generate pressure and pump in more and more water inside the pressure vessel, and that way the product is going to reach desired pressure inside the vessel, and then it's going to be held under those conditions for a certain time, and then the processed product is going to be taken out in the other end, and then it may, since the product packages, everything is maybe suspended inside water, you may have to dry them, and then it's ready for further distribution and handling.
Thank you. And then I'll have another question. In the case of multiple hurdle approach, does the sequence of intervention steps affect the accumulated lethality?
Yeah, that's a good question. And again, there's not much research have been done. And I think, in fact, I think some of those combinations can be very difficult to exactly identify because each product may be different effect. So essentially, there are two things. One is it can be a sequential. So maybe you can, for example, you can provide an irradiation treatment followed by high pressure processing as an example, or you can have a combination treatment. For example, you can combine pressure, heat, and some antimicrobial compound together. So each can be serve as a synergy. And this is going to be influenced by a myriad of other factors, such as the composition, the pH, water activity, and so on. And I think the studies are still relatively infancy, so more studies obviously needed to gain more comprehensive picture.
Another question, it says the reported absence of temperature in literature is mostly for macromolecules present in food, like lipids or water. But this relationship can be used for food matrices considering just the behavior of the major components in it.
Yeah, we have published studies where we can able to predict the temperature increase or transient temperature increase during high pressure processing as a function of the food compositions like water, protein, carbohydrate, and lipids. And I think that probably can be used. Now, a word of caution, I think most of the commercial applications today is pasteurization and typically done under chilled conditions. Under these conditions, the heat of compression effect or the temperature effect on the food matrices are limited. So that's why I think this is not a major issue. On the other hand, as we migrate towards more pressure-assisted thermal sterilization or extended shelf life food, where temperature and pressure play a role, then such relationship become more important.
And do you know if there is any sterilization study focused on food quality and nutrients by high pressure and temperature?
At least there are a number of studies have published in late 90s and probably around 2000 to 2010 on the quality aspects of pressure-assisted thermal sterilization. So one example I can tell is what I was involved. We collaborated with Washington State University, Illinois Institute of Technology, and of course, Ohio State University on developing self-stable eggs, maybe combined with cheese and so on. And we evaluated the quality attributes of the self-stable egg under different conditions. So that's one example. And then over the years, I think people have studied quality impact on fruits and vegetables and other food matrices.
We have plenty of questions. Can it be used for extruded products?
Can it be used for extruded products?
Yeah.
Okay, so I think the key thing is as long as the moisture content is proper, like reasonably high water activity, pressure treatment can be used. Now, the question, of course, is how effective or cost effective if you combine multiple technologies. Extrusion is one, and then pressure treatment and so on. So that's something the individual processor needs to consider.
Can you explain what is hyperbaric storage, and if you think that this methodology could be used in the future?
So hyperbaric storage is kind of being researched by the colleagues at Portugal, Professor George and others. So basically, you use the pressure treatment as a means to store the food materials under high pressure conditions. So the idea behind this is, instead of using refrigeration for extending the shelf life, can we use the pressure treatment and then extend the shelf life of the food by prolonging pressure exposure? Right now, this is primarily done as a research with not necessarily have any commercial applications, but I think with the more and more understanding, the reports I heard from the researchers that eventually one day this can be potential applications. So this is an area I think we likely see some applications in the future. And of course, how you apply this may be different. Either you do this in a mechanical means. The other thing potentially is it possible to store food under different ocean depths? That's another possibility. I think some researchers kind of ask the question. So it is kind of an intriguing concept, but at the moment, I think, to my knowledge, there are no commercial applications.
It says, can you elaborate more on headspace restrictions in case of a PET bottle filled with liquid beverage? He means that, headspace seems to be an important preventive control for spore outgrowth.
Right. So I think the pressure treatment generally prefer vacuum package pouches or bottles and things of that nature. There are two reasons, at least to my knowledge. I think the number one, when you have headspace, you have more volume in your product, in your container. It's difficult to compress because the food water has certain compressibility. The food matrix, on the other hand, the air has a different compressibility. So it's probably going to take a little bit longer to compress the air. And that means your cycle time may increase. So that's number one. The second thing is most of the air contains oxygen, and under these extreme pressure conditions, it's possible the oxygen probably combine and diffuse into the product and can create some oxidative reactions and things like that that may potentially lead to some quality deterioration. So based on some of those reasons, it's desirable to have vacuum packaged products. I also wanted to add that there are researchers and as well as some equipment providers promote the use of modified atmosphere technology. So in other words, they can use inert gases such as nitrogen or argon, things of that nature, and package the product under modified atmosphere. So the first category, the argon or the nitrogen, going to have different compressibility. It may extend the shelf life, but the claim is that it can provide additional quality benefits as well as microbiological safety benefits. But I think these are all probably more and more research is needed to understand the benefit versus the limitations of such technologies.
We have some people from the industry, and they are interested they have like particular questions. Like this one, is any commercial application available at larger scale alternative over 3 tons per hour to liquid egg pasteurizer?
I didn't follow the question. Can you repeat the question, please?
there are like a commercial application available at larger scale alternative over 3 tons per hour. In this case, for egg pasteurizer.
So, like, I think the commercial vessels are, if assuming I probably didn't get the question right, assuming the question is related to the volume of pressure pasteurizer equipment, the capacity is about 625 liters, and per year you can probably have maybe up to 70 million, pounds per year. You can be able to process it. And if you talk about a single hour, depending on the cycle, you may have 7 cycles or 10 cycles of products processed per hour.
Is high pressure processing antagonistic with any other processing treatment?
High pressure processing is antagonistic with any other processing treatment?
Uh-huh.
Okay, so again, this is something probably research is being evolved, and a lot of times the researchers sometimes probably do not report the data when they see negative results. So as a result, you probably don't see much of this type of negative results in the literature, but it's good to report in the interest of benefit everyone in the society. So several years ago, I have seen some research where they have combined pressure and pulse electric field processing, and they did not see any synergistic effect. In fact, antagonistic effect on combining PEF and high pressure on microbiological inactivation. So that can be one example where this may happen.
What is the main cost from expanding from a 40-liter vessel to a 500-liter? Maybe the total force pressure per area, plugs.
So what is the cost as you scale up from 4 liters to 500 liters?
Yeah.
So obviously, the pressure vessels are typically made with like different type of steel, industrial scale steel, stainless steel, and other materials. So those going to probably cost, and then the pump probably going to have a different horsepower requirements. And in order to generate 600 megapascal, that's going to require certain pressure. So the pressure vessel and pump pretty much takes about 90% of the cost associated with the high pressure processing equipment. So that's why maybe small lab scale equipment may be about $100,000. Maybe it's a 10 ml or 20 ml type volume. On the other hand, a large scale equipment may be a couple $1 million because of some of those components of the pressure vessel.
Okay, and this I'll take this as a final question. If you have some more questions, I'll ask Dr. Bala to share with us your. I don't know if you have your email at the end of, or where can they contact you just in case they have any additional questions.
Yeah, they can contact me through my email address. I think let me kind of try to have that at the end.
And my last question is, a lot of people still calling it emerging technology, but it's not an emerging technology now because it's been since the 90s or so. So how should we call it?
So I think if you look at high pressure pasteurization, that became transition into more commercial practice and commercially acceptable technology. So in that sense, I think you may not call that as an emerging technology. On the other hand, if you look at high pressure sterilization or the extended shelf life products, they can potentially still emerging because the research is limited. The other thing is there are various unit operation type applications beyond pasteurization. So, for example, you can infuse ingredients into food using pressure. You can probably extract components using pressure and so on. So those novel applications, unit operations, are still being studied. For those type of applications, you can think about high pressure as an emerging technology. So it depends on the context under which you would like to investigate and you focus on your emphasis.
Okay, well, I still do have some more questions, but I'll kindly ask you, please, to send them personally to Dr. Bala to his email, and I'm sure that he'll happy to answer your questions. And I would like to thank you, Dr. Bala, for your time, for your knowledge shared in this presentation. And thank you all for attending our webinar. We had up to 45 participants from all around the world, India, Mexico, the US, etc. So thank you all for attending this, and thank you so much, Dr. Bala.
Thank you very much. Bye-bye.
Bye.